Let's begin with our learning objectives. By the end of this section, you should be able to determine whether a number is divisible by another, write the prime factorization of a composite number, find the greatest common divisor, also known as the GCD of two numbers, solve problems using the GCD, and find the least common multiple, or LCM, of two numbers. And using the LCM, you can solve some real-world application problems. All right, let's look at this idea here of number theory and divisibility. Number theory is all about the properties of natural numbers. So these are the numbers you're most familiar with, the counting one, numbers 1, 2, 3, and so on. When we multiply two natural numbers, the numbers being multiplied are called factors. For example, if we multiply 3 and 4 together, that equals 12. And so the numbers 3 and 4 are called factors of 12. The rules of divisibility really come from the basis of our numbering system. And since we're a base 10 numbering system, the following rules can apply. These are ways of thinking about how to determine if a number is divisible by a smaller number. Okay. All right. So let's look at if a number ends in 2 or 0, then or any even digit, then the number is divisible by 2. Likewise, if a number is divisible by 5, it will end in either a 0 or a 5. And if a number is divisible by 10, it will end in a 0. Let's check. Consider the number 44,977,680. Is it divisible by 2, 5, or 10? Well, it ends in a 5 or a 0, and so it's divisible by both 5 and 10. And since it also ends in a 0, that's divisible by 2, so it's divisible by all three of these numbers. Yes, Kai.
This is Squidward and Mr. Krabs.
Okay, buddy. So good word, Mr. Krabs. All right, let's roll and check out some more divisibility rules. Okay. So look at the numbers 3. Then if you add up the digits to the number, for example, 21 is 2 plus 1, which is 3. The number is divisible by 3. If the sum of the digits is divisible by 9, then the number is divisible by 9. Then the number is divisible by 9. If the last two digits of the number are divisible by 4, then the number is divisible by 4, and it's the last three that if the number is divisible by 8, then the whole number is divisible by 8. So, for example, 44,977,680 is it divisible by any of these digits? Well, if you add up all of the digits, 4 plus 4 plus 9 plus 7 plus 7 plus 6 plus 8 plus 0, that number is actually divisible by 3. And it's also divisible by 9. So it's actually divisible by both of those. If we look at the divisibility of the last two digits, 4 goes into 80, and so it's also divisible by 4. And then the last three digits, 680, 8 goes into 680. 6 goes in, or 8 goes into 68 8 times. That brings a remainder of 4, and dropping down the 0 brings a 40. And so 8 goes into 40. So it goes in evenly. So it actually goes into all three of these numbers as well. Or sorry, 4 numbers. There are 4 numbers here. All right, moving on. All right, so a natural number is also divisible by 6 if it is divisible by the product of 2 and 3, and 12 if it's divisible by 3 and 4. Okay, so is 44 million, oops, sorry about that, is 44 million, oh, I'm going the wrong way. Is 44,977,680 divisible by 6 and 12? Yes, it is divisible by both of these numbers, since it is divisible by both 2 and 3. And we already saw that it was also divisible by 3 and 4. So it is divisible by both 6 and 12. Okay. Note that there are also rules for checking divisible by other prime numbers, 7, 11, 13, 17, and 19, and so on and so forth. Okay, each of these you can find out by playing around with and actually discover them for yourselves, or you can look them up. Okay. Prime factorization now is one of the fundamental components of number theory, and it's based on the fundamental theorem of arithmetic. And so let's just pause for a minute and think back to if you ever saw the periodic table of elements, you know that each of the elements corresponds to, in some sense, like the smallest divisible piece. It's like the building block of chemistry. And likewise, prime numbers are kind of like the building blocks of the numbers that we know and love. And so the fundamental theorem of arithmetic uh, looks at this idea of the difference between a composite and a prime number. A prime number is a number whose factors are only one in itself. A composite number is any other number that has more than one factor of one in itself. Okay, and so the beauty of the fundamental theorem of arithmetic says that any number can be expressed up to order of the primes as uniquely as a product of primes. So in other words, 2 times 3 is the same thing as 3 times 2. So the ordering of those for the factors of 6 we represented as 2 times 3 or 3 times 2. So it's unique up to the ordering, but 3 times 2 is the same as 2 times 3, both of which are prime numbers, and both of which their product makes the number 6. Okay. So that's really helpful for talking about and looking at the structure of numbers. And one way that we can do the prime factorization is by something called a prime factor tree, or just a factor tree. Okay, so let's look at an example. A prime factorization uses a factor tree. So this is looking at the prime factorization of 700. So you just start with any two factors other than the number in itself of a number. And so in this case, we have 7 times 100. Well, 7 is a prime number, so let's look at 100. 100 could be multiplied by 2 and 50. So we have 2 times 50. 2 is a prime number, but 50 is not, because we can multiply 2 and 25. 2 is a prime number, 25 is not. So now we look at 25, and that's 5 times 5, which 5 and 5 are both prime numbers. So the unique factorization of the 700 up to the permutations of the primes themselves would be 7 times 2 times 2 times 5 times 5. The repeated values of each of these then, of course, means that we could write this more compactly as 7 times 2 squared times 5 squared, or 2 squared times 5 squared times 7 squared if we wrote them in increasing order. Okay, all right. So this is the prime factorization of 700, where the powers indicate multiple factors of that prime number. Okay, let's look at it some more in-depth exploration here. All right, the greatest common divisor, the GCD, is the largest number that will go into two numbers specifically. Okay. We call two numbers whose GCD is 1 relatively prime. So for example, let's see, 12 and 15 have a GCD of 3, but 12 and 13 have a GCD of 1. So 12 and 13 are relatively prime to each other. However, 12 and 15 have a GCD of 3, so they're not relatively prime to one another. Okay. All right. So how do you find the GCD? Well, it's a mechanical process in some sense, where you look at the prime factorization of each of the numbers. So you do the factor tree of each number, and then you select each prime with the smallest exponent in common for each of the prime factorizations. Okay. And then from there, you form a product of the two numbers. And this will be, it feels kind of funny to say it, but it's the biggest, smallest number that goes into both numbers evenly. Okay. All right. So let's look at an example. So finding the greatest common divisor of 216 and 234. So let's prime factor each of these. So 216 is 2 times 108, 2 times 54, 2 times 27, 3 times 9, and 3 times 3. And 234 is 2 times 119, and then, or sorry, 117, I meant, and then 3 times 39, and then 3 times 13. Okay, so if we look at each of the factors in the prime factorization, we see we have 2 to the third power times 3 to the third power for 216, and then we have 2, 3 to the second power and 13 on the right side, okay, for 234. So if we combine them, then let's select the smallest exponent of each of these. So we're going to take 2 to the first power, since 234 has a 2 to the first power. Then we're going to take 3 to the second power, because 216 has 3 to the third, and 234 has 3 to the second. So both of these factors are actually coming from 234. We're taking 2 times 3 squared. 2 times 3 squared, of course, is better known as 18. And so the GCD of these two numbers is 18. That is, it is the greatest common divisor for both 216 and 234. It's the largest number that will go into both of those numbers evenly. Okay. Now, this is often confused and contrasted with the least common multiple. So this is a big number, but it is the smallest number that both of the factors of this number are that you're looking at two numbers whose number is a factor. These two numbers are factors of this bigger number. So it's the smallest, largest number. So that these are confusing because the great GCD is the biggest, smallest number, and this is the largest, and this is the smallest, large number. Okay. All right, so how do you find this one? So it's very similar to the GCD, except for after doing the prime factorization, you take the largest of each of the exponents of the prime numbers, of the factors of the two numbers in question, and then you form a product of those. So I think an example will help illustrate this process, just like the GCD. Okay, so let's find the least common multiple of 144 and 300. Prime factoring 144, you get 2 to the fourth times 3 squared. 300, you get 2 squared times 3 times 5 squared. So selecting the largest factor occurring in each of these numbers, we get 2 to the fourth because 300 only has 2 squared. Likewise, 144 has 3 squared in it, so it's larger than 3 to the first power. And then 144 has no 5s to any power, so we're going to take the 5 squared from the 300. And so we're going to take each of these elements together, and that gives us then forming the product of those 2 to the fourth times 3 squared times 5 squared is 16 times 9 times 25. And so the least common multiple between 144 and 300 is 3600. Okay, in other words, that is the smallest number that both 144 and 300 will go into evenly. Okay. All right, let's look at an example of how you might use the LCM to solve a problem. Okay, so let's just assume that we have a movie theater that runs its films kind of continuously, meaning as soon as it ends, it goes back to start playing it again, and they're only showing 2 movies. Okay, so one movie runs and it's 80 minutes long, and the second film runs and it's 120 minutes long. Okay, the theater opens and plays the videos at 4 o'clock in the afternoon. And you want to know when is the next time that both movies will be starting at the exact same time. Okay, so our strategy is to do this. We're going to find out what is the LCM in minutes of 80 and 120. And then we're going to look at, after adding those minutes to 4 o'clock, what time we have. So that's our strategy. So let's find 80 and 120. Let's find the LCM of these two numbers, the least common multiple of these two numbers. Okay. And if we did that, we'd find that the LCM of these two numbers, is, well, 80 can be written as 2 to the fourth times 5, and 120 can be written as 2 cubed times 5 times 3. So we take the largest of each of these. So we'll take 2 to the fourth, we'll take a 3, and we'll take a 5. And so that gives us 240. So the LCM of 120 and 80 is 240. And so if we divide that by 60 to convert it into hours, 240 minutes is 4 hours. Adding 4 hours to 4 p.m. means we would be at 8 p.m. So after 4 hours, both the theaters would be showing the two films, would be starting over at the same time, at that time. Okay. All right. So that's a strategy then for using LCM in a problem that you might encounter in the real world. Okay. All right. I hope that was helpful, and I look forward to seeing